reasoning large language models have recently achieved state-of-the-art performance in many fields. However, their long-form chain of thought reasoning creates interpretability challenges. As each generated token depends on all previous ones, making it computationally harder to decompose. We argue that analyzing reasoning traces at the sentence level is a promising approach. To understand reasoning processes, we present three complementary attribution methods. A black box method measuring each sentence's counterfactual importance by comparing final answers across 100 rollouts, conditioning on the model generating the sentence or one with a different meaning. A white box method of aggregating attention patterns between pairs of sentences. So let's just first talk about what that means. So we have a reasoning model. It has a question, then it produces a bunch of reasoning chain of thought, and it arrives at an answer. And we want to understand the reasoning, not at the level of maybe the individual parameters and so on, which is common for mechanistic interpretability, which at least these guys up here are masters of, but instead at the level of the reasoning chain itself. So in mechanistic interpretability and of course in other fields, this idea of counterfactual causal analysis is important and has been used a lot. So what they're saying here is maybe we will take a specific sentence in the chain of thought and we will just try to alter it. Let's say it was a mathematics question and they said, oh, actually, then we have to use this famous lemma ABC. And then they remove that and insert another sentence that says, okay, I guess we can just go forward or something. And it doesn't mention that. Then and then you continue and see like what does the language model generate in the chain of thought after that sentence, and it will arrive maybe at a different answer. So that's the first one. And a white box method of aggregating attention patterns between pairs of sentences. So this is more in the white box. So white box, they mean that they look into the model, so that's like kind of mechanistic interpretability related, and aggregating attention pattern. So for each sentence, there will be some kind of attention matrices that describe the relationship between individual tokens in the sentence, and then they have some kind of idea for how to compare the different sentences and these patterns. So between which identified broadcasting sentences that receive disproportionate attention. So broadcasting sentences. So what does that mean? That means if they look at attention. So attention, you're looking at one token is looking at the previous token via a query vector going to key vectors, and this is of course happening a bunch in all the layers and in all the heads of the different layers. So you could somehow try to see, okay, is there some sentence that is being attended a lot to? So the key vectors for the sentence are being like targeted by the queries of some later sentences, and they're gonna have to somehow like do that. So they call that receiver attention heads. That there are certain attention heads. So in each layer we have a bunch of attention heads that like, yeah, I will not draw it. It's no. But they have a bunch of attention heads in each layer, and they will be looking at then mechanistic interpretability has worked a lot with this idea that there might be different heads that are responsible for different things, and therefore this is then the idea that there would be some heads that would be responsible, and within that head there you would have attention matrices for that show this thing where the broadcasting sentences are being attended to. And then 3, a causal attribution method measuring logical connections between sentences by suppressing attention toward one. Logical connections between sentences by suppressing attention toward one sentence. Each method provides evidence for the existence of thought anchors, reasoning steps that have outsized importance and that disproportionately influence the subsequent reasoning process. These thought anchors are typically planning or backtracking sentences. Okay, so the last thing, we'll have to see exactly what they mean by that. We provide an open source tool for visualizing the outputs of our methods and present a case study showing converging patterns across methods that map how a model performs multi-step reasoning. The consistency across methods demonstrate the potential for sentence-level analysis for a deeper understanding of reasoning models. So, training large language models to reason with chain of thought has led to significant advancement, traditional mechanistic interpretability, however, blah, blah, blah. A core step in many interpretability to compose a model, natural decomposition into individual sentences, operate at a very level of abstraction. Sentences are less likely to conflate reasoning steps and may serve as an effective target. Summary of our three methods. Prior work has established that different sentences within traces perform distinct functions. Backtracking sentences boost final answer accuracy. Other research has distinguished sentences based on whether they retrieve new information. So, execute deduction. Hence, reasoning may follow an overarching structure where sentences can introduce or pursue high-level computational goals, yet we focus on what we thought anchors, critical reasoning steps that guide the rest of the reasoning trace. We provide evidence. First, in section 3, we present a black box method for measuring the counterfactual impact of a sentence. We repeatedly resample reasoning tracing from the start based on that's simple, not easy, simple idea. Via the resampling approach, we can distinguish planning sentences that initiate computations, leading to some answers from sentences performing computation necessary, but which are predetermined. Second, in section 4, we present a white box. Third and finally, in section 5, we present methods that measures the causal dependency. Setup, sentence taxonomy, problem setup, plan generation, fact retrieval, active computation, uncertainty management, result consolidation, self-checking, and final answer. DeepSeek R1 distill Quen. So this is a model where they took it's made by DeepSeek. So what am I doing wrong here? Sorry. What the R1 did was not R1. DeepSeek did was they trained R1, right? And they trained it using reinforcement learning to reason, and then they distilled it to Quen 14b. So Quen is a model made by Alibaba, and they have some models already. And then they take R1 and generate a bunch of reasoning traces, showing Quen 14b how to do it, and then they distill it using, for example, supervised fine-tuning or something. So that's the model. It's like 14 billion, so it's okay enough to work with. And then they describe how they sample the sequences, and then they're considering the math dataset, which is a dataset of math questions, and it also has associated ground truth reasoning traces, but I'm fairly sure, yes. But they will of course look at then the reasoning traces generated by this model on this thing, and specifically targeting 10 challenging mathematics questions. So what they did is they look at all these questions in this math data set, and then they generate like attempts to answer it, and some are easy, some are harder, and they are looking at those, a selection of them, 10 of them that are medium hard. They call it challenging, and for each selected problem we generate one correct and one incorrect reasoning trace, producing 20 responses. Okay. 144 sentences. And we focus only on sentences before the resampling method indicates the model has converged on an answer. And then I wonder which code base they're using for this. Some sentences matter more than others. No, sorry. We focus on the sentences before the resampling method indicates the model has converged on an answer. So if you consider this, let's look at the sentence level. You have a bunch of sentences. This is your X, this is your question. And then you have y1, y2, y3, y4, y5, and then you have answer A. And then these are sentences now, and you can then look at what if you go here. Whoa. What if you go down here? Then you will get maybe the same answer. Okay, this is not the best place to draw. Maybe here. So this is your question, and your model can produce these chains. And these are thought of as sentences, so that's why I would have them as circles, and then they produce an answer, A. And maybe the answer is red, A1. And you can use this model anywhere to generate, so you say, oh, I'm gonna predict next tokens from here, and I'm gonna then generate sentences and arrive at some answer like that. And you can see that if you have had a lot of thinking, then maybe by the point you are here, then you will already have found the answer or something. But imagine that you're starting earlier, this one. If you're changing now this into I need to make some kind of idea that I'm changing the sentences, right? So I'm changing the sentences from this to this, and that then happens. But if I'm here and change it to these, so I'm going like this, then I might get often, or maybe not so often. It depends on there will be some distribution over the answers. So for each point, each thing, I can then get a distribution over the answers. So if it was like, what is Bob's daily salary? Some kind of math question, and here you had $500, and here it's $200 and 20. Then for each position you are in, if you substitute, so with respect to some substitution distribution, no, how should we think about it? We could think of it in different ways. So there will be one that's just with respect to the model. This here, if I am here and I generate a chain, then this generation from the sentence down here, it's stochastic. So it will generate some answers, and this will lead then to an answer distribution. You could call that QA given this thing. So this thing would be the chain of thought and everything. So it will be like this. Maybe we could just call it x hat y less than t, where t is like the sentence you're at. And then there will be some kind of distribution if you say maybe I think I would rather say x, and then you're going down to t, yt minus 1, etc., y1, because then you can say q of a given x hat y less than t, yt. So here I mean the concatenation of all of this. Then there will be a distribution, and then there will be a counterfactual distribution if you go down here, but you swap this one with something else. So there will be a Q A given the question, the reasoning trace before, and the final new sentence. Okay. That was a bit long for explaining that, but then where are we? So some sentences matter more than others. Which ones matter depend on how we define and measure importance. We frame sentence level importance as a question of counterfactual influence. How does including or excluding a sentence affect subsequent steps, and the model's final output? So you could also be interested in not only what you end up with here down with the A's. You could also be interested in what kind of sentences are there in here in between. That's what they said, that like there's some kind of logical connection. Maybe some sentences, they are like special because they not only change the distribution over answers a lot, they also change the something about the sentences. Oh, no, I missed that. So, some sentences matter more than others. In earlier work, importance has often been approximated by forcing the model to give an answer before completing its full reasoning trace. We tested this strategy. For each sentence in our examined model responses, we interrupt the model at this point and append the prompt inducing it to give a final answer. So what they're writing here is, therefore the final answer is boxed curly brace. That's because boxed curly brace is like Quen models and many I don't know, other models like what's happening here? Where do I need to click exit pen mode? There. So they all end up saying boxed and then $200, for example, something. So they blah 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 boxed like that. So if you just stop here, you just go down to some sentence, and then you do not try to just see what the model does when it predicts the next tokens and everything and comes to an answer, but you just say here, therefore, da da da. Then you can know, in a sense, something about the information it has about the answer or something at that point. To generate distribution of answers linked to each sentence position. So again, that's what I'm talking about here. They will now go for each of them. For each one, they will have a distribution like this by having this ending where it says therefore. So that's good. So now you have something like Q, A, T, where T is time, and you have the prefix. So you could call this Q forced or something. And now I close the other thing. Main. Okay. The taxonomic, we measure the KL divergence between the distribution before sentence I has been stated and the distribution after. So that means you have these two, QAT and QT plus 1, which would then be X. That would be a bit hard to read. Down here would be X and then Y all the way up to T, and then yt plus 1. So from this point and this point, both of them you could try to autocomplete, like force it to give an answer, right? So these will be two distributions. The KL distribution will measure the divergence from this to this or this to this. It's not symmetric, but you could use it as a measure of how much it changes and use that as an analysis. So in general, we would expect that, what would we expect? We would expect that there's some kind of progress, right? Because if you're reasoning, then you're going to a point, and you're hopefully this thing down here is a good distribution. So right before you have reasoned this much and you then try to force an answer, of course it doesn't itself force it an answer, but you could try to force an answer and you would probably get roughly the same answer as the answer that it would give. It would maybe not say therefore blah blah, it would say okay, so the answer is, or something. And I'm still new to this, a bit new. Yeah, so you would have a development, of course, in the KL divergence, but for each point in time, there would be some change in the distribution. So if you imagine it, you have this space of distributions. Here is the good distribution that you end up in the end. Then if you force it immediately, you would be here. And then as you're reasoning with a chain of thought, you're approaching a distribution Q, let's call it big T, which is just like the final end. And here is QA1. And I just will not write the conditioning. So that's what is going on. And then at each step, you are like having some kind of KL divergence to the previous step. And we might not have a good idea about what's happening there. If maybe it's a bit bigger or a bit smaller. Like you would maybe think that if you introduce something very important, you have a very big insight, then you would kind of make a big jump in the conclusion. Like you have, bam, you think, oh, I could use, or you said, oh, but Bob's sister did not help him get the salary, and then it realizes that actually this $500 is not as likely as you thought. But it could also be that just because you have an insight at some point here where the change you it does not mean that the the um, the force distribution changes. It might just be that if you counterfactually had another thing going on at this point, then you would not then you would have a big change, but you still might need to think through all the implications of your insights and go down here, and then you force it down here. So what does it say? The taxonomic categories reveal that active computation statements produce the greatest distributional shifts. Active computational statements. So that means just because you have an insight that you need to think through something, you still need to compute it. You might say, oh, Alice's Bob's friend did not blah blah blah. So therefore, that was it. Like, oh, but Alice did not do this. That's one sentence. Then the next is, so therefore we subtract $300. So therefore we are now at $200. So therefore the answer is $200 or something. So 500 minus 300 or whatever. This might be an active computation, and this is a much more this is the one where the force distribution over answers changes more than this one. And once again, I closed it. Okay. This aligns with prior findings that reasoning models update their beliefs throughout the trace, and trace suggest immediate calculation alter the model's answer responses. However, active computation steps may not provide a comprehensive view on importance, as they may be predetermined by upstream statements. So that's what we said. Counterfactual importance. A natural limitation of the forced answer approach is that sentence S may be necessary for some final answer, but consistently produced by an LLM late in the reasoning sentence trace. What does that mean? That means that as long as you have this insight that Alice is actually did not help with the salary, then you will in all cases end up making the calculation $500 minus $200. So this is important. It's important to do this step. But if the model always produces this step when it finds out that actually Alice does not help Bob with the salary, then surely this sentence is more important. Therefore, we should think about this. But it does not change the force distribution because he still needs to compute. And therefore, we need to talk about counterfactuals, where we're changing it to another. Accuracy over 100 rollouts at each sentence. For A, one correct, and B, one incorrect base solution. Forced answer actually will be low for all sentences that occur before S, not allowing the importance of these are determined. Consider a rollout which consists of a sentence. The resampling importance metric, which is the KL divergence between the final answer distribution in the two conditions. One where we make the change. So sentence S causes it to be incorrect. Below for only the occurred before S. So SI yeah. So this is what we drew before. Okay, it was teal draw that I missed. So this is this change that I was saying here. You're making some you're making some kind of substitution, and this is called S. This is called SI, and you're looking at the force distributions. Not the force distribution, sorry, the rollout. The rollout. So you roll out from here, and you roll out from not intervening. You get two distributions over answers. You take the KL divergence. Man, I have to be more slow with this pen. Semantic filtering. The problem with resampling importance is that in rollouts resampling, if TI is not identical or similar to SI, we do not get much information whether SI is important or not. So T is the following steps, I think. The steps after, yeah. Then it's identical. We do not get much information whether it's important or not. Therefore, we write S is not equal to T if two sentences S and T are dissimilar, defining having a cosine similarity less than the median value across all sentence pairs in our dataset when fed into an embeddings model. Therefore, we define the counterfactual importance differently by conditioning on Ti not equal Si, that is this thing. So what does that mean? That means I have to go away from my ugly F here. So what are they saying? We have an X. This is a question. Let's use the same notation as they have. S1, S2, S3. Great. These are the sentences and the question. And now we're going to make a change. So we are going to go here and say S4. Then we are going to look now at the traces here and consider that we actually do not have, do we have one? Yes, we generate now 100 of these following. I think they can of course have different number of sentences in the following, but they will end up with a bunch of answers, and it will generate a distribution. $200, $500. And then we will also do it here. 100 rollouts, and we get another distribution here. $50. This is called Q of A. I will not call it any name yet. But then their point is, if we have similarity here, so if these are similar, then we somehow but we still should be interested in them. But at least they will say, no, we should actually think about this. Consider these ones, they're not so similar. They're similar. So in that case, we're not so interested in them. We're more interested in the case where we make a change and we also get something that is not like the sentences that was here. SI. So these are called SI. So this would be S4. I just do not know which one they care about. Maybe they do it paired or something. S4, and this would be called T4. And this would not be called, as I wrote here, S4. I would be called S3. It would just be called S actually. S. And now what can you do? You can take an embedding model. So this is like a bit like a transformer. You take how can I write it? I'll just write it mathematically first. So you take a sequence in, so you have a vocabulary, sequence of tokens. It has some length, t. It will of course variable, so maybe it should not be like that. And it will just give you a vector that represents this sentence. So you could, let's call this embed. So I will call it embed. I'll call it E. So you can write something like E of this whole sentence here. So you will write, no, of this sentence. So E of S4. S4. This is your sentence that followed. Or was it the one that followed? Ah, this was what I misunderstood. Okay, they're interested in these two. These two. S3 and S4. So they're interested in S3. And it is a vector in RD. RD. And then they also have an embedding of S, the counterfactual one. That makes a lot more sense. S. And it's also in RD. And then they can look at how similar the vectors are. So the embedding model is made so that vectors are similar if they have the same meaning. This is just how it's programmed to be. Maybe it's like indirectly, maybe it's trained to have the property, or maybe it's an indirect property. For example, it happens to be the way that whatever. This is what it does. And then it makes sense, because here you say, like, let's say we have the examples from before. We have a math question, and here S3 would be something like, but wait, Alice did not give me $20. That if you then change counterfactually to another sentence S that says, but wait, my friend Alice did not give me $20. Then of course these would be very similar, and we would want to take that into account. We would want to think about it versus there could be another where it says, but actually all my friends gave me $20, then that would be very different from Alice. And if you have a good embedding model, hopefully there could be a big distance between these two. So what do they say? They say we're conditioning on this. We're looking only on the case of this. So it will be the same calculation, but it will just be different in terms of the analysis. What kind of stuff are we looking at? Okay. So, since we resample all steps after a given sentence S, we avoid the aforementioned limitation of forced answering. Across the dataset, we find that plan generation and uncertainty management, backtracking, sentence consistency show higher counterfactual importance than other categories. I still do not quite understand what is going on with the selection. Is SI So it's somehow they're looking at this is one where they roll out, and the other is just they're keeping it. So they're not, yeah, but the SI is probably just the sentence. Yeah, the sentence, the SI is the sentence that they actually have in their examples here, and it's a very small data set they have. It's a very small data set they have, but so they are not in essence changing it like this. It's more that they are looking at this thing. They're more looking like this. This is T3 in a way. So they're taking a sentence and then they're considering this sentence. Is this sentence important? Well, it is, because let's not use sentence and just look at what the model would otherwise maybe generate. So that would be relative to looking at the answers that are wrong. It's still cool, but I think there are many experimental choices here that you could make in what you care about somehow. But yeah. Sentence to sentence importance. In addition to estimating sentence effect on final answer, we extend our framework to quantify its causal influence on each individual future sentence. This sentence level attribution helps uncover the structure of the model's chain of thought, which sentences initiate subroutines, influence future claims, or attract as attractors for subsequent steps. We estimate the kind effect and importance on a future formally with the importance of S1 on a future one is the probability of the future sentence being in the coming chain minus the probability of the sentence being that in the future, that sentence being in the future chain when we do not have TI be like that. So this all makes much more sense now. We already had this idea that is actually about starting from here. So there will be all these different ones. You go one step back, you roll it out, and you just care about the cases where the model rolls out to some S that is not similar to the one you step to. And if you do that, then you can then look at the probability. So this is as future. Let's call this down here as future. As future is a specific sentence. Let's say that it was as future was equal to S6, and it was. So therefore 500 is equal to 200 plus 300. This sentence, it is somehow related to this sentence up here, this sentence S3. In which way? It's related if it only occurs when this sentence occurs. If we instead interchange it to get to another sentence, where we say, as we said, like, but actually all my friends gave me $200, which is a very dissimilar sentence, then we never go down here and find a sentence that is, so therefore 500 is equal to 200 plus 300. And therefore, this sentence must be related to this sentence. The only thing that I am worried about is, are we thinking about it verbatim? Because so therefore 500 is equal to 200 plus 300. We do not need that this sentence should always be in here. We somehow want also to think about similarity in that case. But maybe that's the idea of probability. So okay, I think I'll take a break here.